graph, and I want the limit as x approaches positive infinity. Okay, remember when we did limits, that is what y value it approaches. So as I approach positive infinity, the y value it looks like it's going to hit is actually positive 3. Okay. If I want the limit as x approaches negative infinity, if I move along here, the y value it looks like it will approach will be positive 3 as well. Okay, and so if you notice we have a dashed line there. What do we know represents a dashed line? An asymptote. So actually this graph has a horizontal asymptote at 3. So there's actually a correlation between horizontal asymptotes and limits, and we will talk about that as we progress through the lesson. So first of all, the definition of a horizontal asymptote, you already have this on your sheet. The line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of the function equals L, or if the limit as x approaches positive infinity of the function equals L. So on the previous slide, since the limits were 3, you know you have a horizontal asymptote at 3. So let's go ahead and look at the following. It says find the limit as x approaches infinity of 5 minus 2x squared, 2 divided by x squared. So go ahead and graph that for me. If you want to graph it in a good window is the Z standard window. Z decimal will not work here.
Whoa.
Okay, so if you look at that, it looks real similar to what the previous slide was, except for, okay, at 0 it's undefined. So the graph looks, let me go ahead and write this up there. The graph looks like this, where at 0 it's undefined. It also looks like it has a horizontal asymptote. What do you think that horizontal asymptote is?
5.
5. Why do you say 5? What? That's where it look. Yeah, that's in. And if you look in the original equation, what I want you to do is look at this original equation. Why do you think it's 5?
Because of the number 5.
Because of the number 5. You're exactly right. And there is a way that we will find these algebraically too. That if we just look at the function, we're going to know. Boom. That's the limit is 5. We know there's a horizontal asymptote at 5. So let's go ahead and look at the next slide. It says find the limit. And this one's as x approaches positive infinity. So as x approaches positive infinity, if I graph this, what does it look like my y value will be at positive infinity?
2.
Why do you say 2? It looks like it from 2 from the graph. Does anybody else think it's 2?
No.
Well, actually, the limit is 2. Okay, from both the left and the right. There is a horizontal asymptote at 2 as well.
I can see that.
Okay, now once again, there's some algebraic ways that we can find that. And that's what we're going to look at right now. So you have these guidelines written down. And so first of all, it says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So basically what they're saying there is if you like have an x over an x squared, or like an x over an x cubed. Okay, so you have a higher power in the denominator. Okay, number 2, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. So basically what ends up happening there is you cancel out your variables and you're left with whatever the numbers are. And then finally, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So an example would be like if you have an x cubed over an x, okay? X to the 4th over an x cubed. Something like that. That's what they're meaning by degrees. And so we have 3 problems right there that just want you to find each limit. They want you to do this without graphing. So we're going to look at each of those 3, and we're going to apply the guidelines up above. So first of all, let's look at the first one. I have 2x over 3x squared. So all you're concerned with now is your highest power in the numerator and your highest power in the denominator. You're not worried about the others. Okay, you're worried about highest power only. And so which of the 3 does it fit? Does it fit the first, the second, or the third? The top one. So the top one says the limit will be 0, so therefore, there you go. So what that means is that there is actually a horizontal asymptote at 0 as well. And we would see that if we graphed. So let's look at the next one. The next one, once again, we're only looking at highest powers. You notice that those are the same. So as a result, we're going to get rid of the x squareds and we're only going to look at the numbers. So my limit there would be 2/3. So on that previous slide, when it was 2x minus 1 over x plus 1, that's why our limit was 2. Okay, because the x's cancel and you have 2 over 1. The third one, what do we have here?
Top one's greater, so
Top one's greater, so the limit does not exist. So what does this probably do? This probably goes to infinity. So if you were to graph this, this is one that will go to infinity, or negative infinity. So let's look at the next slide, find each limit. Now if I look at this, let's just do this without typing it in. I'm going to look at the highest power here and the highest power on the bottom. Now the question is, what actually is the power on the bottom?
1.
It's actually 1. Because if you take this, oops, let me use a pen. If you take the square root of an x squared power, that's like an x to the first. Okay, so really those powers are equal. So this is one that you're just going to look at the ratio of the coefficients. So it'll be 3 over root 2. Okay, so that'll be it.
Wait, you can't have a numerator.
I know, so you would answer 3 root 2 over 2. You can answer both.
I was just making sure you were following your own rules.
Yeah, I know. They're the same thing. And in that case, what you're doing is you're looking at the ratio. Now, on the next one, what's different from the first one? This one's negative infinity. So the only thing different that that does is that actually makes your answer negative. So it will be negative 3 over root 2. Okay? Or negative 3 root 2 over 2. Okay?
We have to turn the sign.
All right, so let's go ahead and look at the limit of sine.
It's greater than the bottom, so it's equals.
The first, no, A.
Yeah, it's greater than the bottom.
What's greater than the bottom?
There's just a 1 that
You need to make sure you're in radian mode.
I've
supposed to be-
been
If you're in degree mode, it won't work. You need to make sure you're in radian mode. Now, if you remember the graph of sine, this is back from trig. The graph of sine is a function that oscillates. Okay, it oscillates between what 2 values? 1 and negative 1. So this graph of sine looks like this. So is that going, oops, sorry, is that going to have a limit? No, it's just going to keep going back and forth. So this one is actually a DNE.
How do we do that algebraically though? Just simple down.
Yeah, you have to remember what the graph of sine looks like. Is that for, there's like no rules on that one.
There's no rules.
So let's go ahead and look at the next one.
You got it? It's
What does it look like it does? Kind of.
it's a lot wider. It's got like an aspect. Like getting smaller.
It like is getting smaller, right?
Yeah. Oh, mine.
It just has
Mine looks like yours.
That's eventually what it's going to do.
Why does mine not grow? Mine's like a little one. Yeah, that's how mine looks.
You might need to make it bigger on your graph. Okay? A good, let's try -50 to +50. And for y min and y max, let's go -2 to +2.
For which one, -15, +15 for what?
Okay, it kind of looks like a heartbeat that gradually is decreasing. We wouldn't even need to go -50 to +50. We could actually probably go -30 to 30. Yep. So gradually, what does it look like it's going to approach as it goes to infinity? 0.
Mine looks like this. And mine zoomed in. It didn't look like that.
Yeah, mine's
Whoa.
how you size it?
Okay, now it looks like yours.
Alrighty, so that's basically limits at infinity. That's section 5. Okay, you have your homework, which is 3 through 8, 17, 18, and then 21 through 32. On 3 through 8, that is a matching graph. So what you're going to do is look at the functions in each of the problems, see where their horizontal asymptotes are, and then go ahead and figure out which one of the two correlates. On 17 and 18, those are find each limit using those properties or those guidelines. And then 21 through 32, once again, is the same thing as well. You can either graph them or use the properties. Not a long assignment, won't take you a lot of time. So, probably expect a quiz Monday-ish again.